Okay, good evening, everybody. Before we start today's session, I do have a couple of announcements. Our own work assignment is due on Sunday, March 2nd at 11 p.m. That is for Chapter 19, end of Chapter 19 questions in R. That is due Sunday, March 2nd at 11 p.m. I also want to remind you that the second class exam is scheduled for next week Thursday, that is March 6th. Okay? And that exam will cover chapters 17, 18, and 19. Okay, for today's session, we are going to continue our discussion on the chemistry of aldehydes and ketones. If you recall, when we left on Thursday, we were discussing we started discussing nucleophilic addition reactions to carbon-oxygen double bond. Specifically, we started with the formation of star and ketals. So we are going to take off from this topic today. So we have nucleophilic addition to carbon-oxygen double bond. If you recall, we started with cyclohexanone. And we told you that if we take an alcohol, in this case, methanol, in the presence of some acid catalyst, say we use hydrogen chloride in this case, that we will get this. In which what we've done here is to add the element of methanol, the alcohol, across the carbon-oxygen double bond, in which case the oxygen of the methanol is acting as a nucleophile, and the carbon of the carbon-oxygen double bond is acting as an electrophile. So if you see here, in essence, let me use a different color here. In essence, what have we done? We added the methoxy to the carbonyl carbon, and this hydrogen here is right here. So it is in essence the addition of the alcohol across the carbon-oxygen double bond. And so we call this a nucleophilic addition, because what are we doing? Adding a nucleophile to this carbon right here. And then we told you we could take this further if we now take another mole of methanol, also in the presence of an acid catalyst, now we could get this. Now, the first product that we got here as a result of nucleophilic addition, we call this an emi-ketal. Okay. The emi-ketal is that in which you have the alkoxy group attached to a carbon atom, and that carbon atom is also attached to an hydroxy group. Okay, in this case, that carbon is also attached to two carbon atoms coming from the ketone. So we say this is the emi-ketal coming from the reaction of the alcohol with the carbon-oxygen double bond. Now the second product here, we call it the ketal. Now see, in the ketal you have two alkoxy groups. You have two alkoxy groups attached to the same carbon atom. And that carbon atom is also attached to two carbon atoms. Now we also told you we could perform a similar reaction with aldehyde. Say for example, if we take this specific aldehyde here, take methanol in the presence of an acid catalyst, okay. So in this case, we are also adding the alcohol across the carbon-oxygen double bond of the aldehyde. In this particular instance here, we see I have hydrogen here. We call this the emi-acetal. In the emi-acetal, both the alkoxy group and the hydroxy group are attached to the same to a carbon that is attached to an hydrogen atom and also attached to a carbon atom. In other words, the emi-acetal is coming from an aldehyde. Now, so this part of the reaction here, this is the nucleophilic addition reaction right here. Okay. Now, we could also take another mole of the alcohol, in the presence of an acid catalyst. Now we get what we call an acetal. And also, we told you that we could use the acetal or the ketal as a protecting group, particularly if you form the cyclic ketal or cyclic acetal. For example, take this. Take this molecule here. And now we take this diol in the presence of acid catalyst. This is ethylene glycol, by the way. That is the same liquid you use for your antifreeze in your car. Okay, you take ethylene glycol in the presence of acid catalyst. So we form the cyclic ketal. Now, if at this point we now want to reduce this extra functionality here into an alcohol, we could do that now that we have protected the carbonyl right here. So you could take LAH, which is lithium aluminum hydride, followed by dilute acid, and you reduce the ester to a primary alcohol, and you still have your acetal in place. So at this point, if we now add dilute acid with a little bit of heat, we will be able to regenerate the carbonyl of the ketone. So in this case, we have used the ketal here as a protecting group. We could similarly do the same thing if we had to protect the carbonyl of an aldehyde. Yes. This here? Oh, ethylene glycol. This here, the one with the diol. Okay, that's ethylene glycol. Okay. Okay, so that was the first example I gave you of nucleophilic addition to carbon-oxygen double bond. So we call this example number 1. Okay? Yes. Yes, I gave you the mechanism. Yes, you do need to know the mechanism. It's very important. If you recall, I gave you the mechanism before we left on Thursday. Okay. Okay, now let us look at another example of nucleophilic addition. Let us call this number 2. We'll call this addition. All of you should be familiar with this. Addition of Grignard reagent. To give alcohol. Okay, let us call it example A. For example, we could take this Grignard here, and we add formaldehyde, step 1 and step 2 hydronium ion. Here we get I believe we've done the mechanism of this reaction before. Okay. If you notice here, all we are doing, if you think of the linear reagent as a source of your nucleophile, the carbon that is attached to magnesium is negatively charged. Of course, then you have your aldehyde. Okay, so what we have here, all we are simply doing is the nucleophile is adding to the attacking the electrophilic carbon of the carbonyl, and you get your intermediate. Now it is now this alkoxy intermediate that we now add dilute acid to. This here will grab this proton here, releasing this pair of electrons to oxygen to now give you alcohol. Okay, so this is the mechanism of this process. Okay, we could also use, and in this case we are forming a primary alcohol. If you react the linear with formaldehyde, this is formaldehyde right here. This here, right here. Okay, other examples of the linear reacting with carbonyl. Call this B, 2B. We take the same grignard, this time if we react this with a primary alcohol, primary with an aldehyde. Sorry about that. Step 1 and step 2, I don't know. Okay, you see the mechanism here. Nucleophile attacks this carbon here, pi electron goes to oxygen, and then you protonate the resulting alkoxide. So in this case, the grignard will react with an aldehyde to give you a secondary alcohol. We could also, call this 2C, react the grignard with a ketone. Take this ketone here, which is acetone. This molecule here is called acetone. And then step 2, hydronium ion. And what do we get? We get in this case, the Grignard will react with a ketone to give you what kind of alcohol? Tertiary alcohol. Very good. Okay, and also you should be able to write the mechanism for that reaction. It's similar to the mechanism that will give you for the reaction with formaldehyde. Yes. Yes. And with the Grignard. Yes. Okay. Okay, so now let us give you example number 3. Still under nucleophilic addition to carbon-oxygen double bond. So we call this addition of hydrogen cyanide to give what we call cyanohydrin. Just take the same ketone. Keep in mind, even though I am using this same example, this applies to all ketones or aldehydes, the carbonyl of ketones or an aldehydes. Okay. So what do you have here? HCN hydrogen cyanide who add to the carbon-oxygen double bond of a ketone or aldehyde to give you okay, so what have we done here? In essence, we have added the hydrogen cyanide across the carbon-oxygen double bond. In which case, the cyanide here is acting as a nucleophile, and of course, the proton then added after the addition of the cyanide to the electrophilic carbon, which is this one here. So in essence, this is the mechanism for this reaction. Okay, just a simple case of nucleophilic addition. That's electrophilic carbon is attacked. The pi electron comes to oxygen. You see that in all of these nucleophilic addition reactions, the mechanisms are basically all the same. Okay, and at this point, the alkoxide ion that is formed will now be protonated by a proton from the hydrogen cyanide. So this comes here to grab the proton. Okay. and then you form your cyanohydrin. Just called this A-cyanohydrin. A cyanohydrin is that molecule in which you have the nitride is attached to the same carbon, and that carbon is also attached to an hydroxy group. Okay, so we form a cyanohydrin. Now, this cyanohydrin that is formed could be very useful in synthetic design. For example, you could take this and use fairly mild dilute acid to oxidize the nitride to a carboxylic acid. So this is a very nice way of going from a ketone to a carboxylic acid. You could also take the cyanohydrin and react with lithium aluminum hydride, LAH, followed by dilute acid. What that gives you is a primary amine, Okay, we are going to discuss that primary amine in later chapters. I believe that will be in chapter 22. So anyway, you can see here the utility of these reactions. Keep in mind we start this with the nucleophilic addition to carbonyl, and then you could the product that you obtain you could use for subsequent synthetic reactions. Okay, so that was number 3 under nucleophilic addition. So you want to go back? Will you go back? You want me to go back? Okay. Okay. Number 4, still under nucleophilic addition. Addition of phosphorus yelate. Now, this is a brand new reaction for you guys. All of the reactions that we have been doing so far, those are reactions that we've done before. So this is new. Addition of phosphorus yelate to give carbon-carbon double bond. In other words, forming an alkene. If we take the same keep in mind this reaction also applies to aldehyde, carbonyl of aldehyde. And we take this. This here, we call this phosphorus yelate, in which you have phosphorus is attached to a carbon that is negatively charged, and the phosphorus atom is positively charged as a formal charge of +1. Out of this here, this pH equals to benzene. Okay. Now, this particular reaction, you react a phosphorus yelate with a carbonyl of a ketone or carbonyl of an aldehyde. This is a very useful reaction indeed. You now obtain this. So what do we have here? What have we done here? We have essentially replaced the carbon-oxygen double bond with a carbon-carbon double bond. That is what this yelate is doing. Yelate is acting as a nucleophile attack this carbon here. Okay, and subsequently you are going to generate the carbon-carbon double bond. Okay, so this is one of the few reactions that allows us to make new carbon-carbon bond. Okay, we know that Grignard will form a new carbon-carbon bond. We know that Gilman will make a new carbon-carbon bond. So you should add this to your tool of those reagents that allows you to form a new carbon-carbon bond, which is the yelate. And this particular reaction we refer to as a Wittig reaction. And very often we refer to the yelate as a Wittig reagent. Okay. Now we could use all kind of phosphorus yelate. For example, we could do this. Yes.
What is the phosphorus you put in your hand for?
Huh?
What is the phosphorus you put in your hand for?
Right here? Yes. Yeah, this phosphorus right here. This. Huh? The pH? Oh, yeah, the pH is benzene. That's what I have here. You know that our phosphorus is attached to 3 benzene. Okay? Okay. We could do this. We could take that our phosphorus yelate, and what do we get? You get that? Notice what have we done here? This here, this carbon of the phosphorus yelate is attaches itself to this carbon here, and eventually you are going to now